Did you know that at this very moment, massive antennas around the world are capturing signals from space that your eyes could never see? Right now, these incredible instruments might be detecting the birth of a new star in a distant galaxy, or witnessing the dramatic final moments of a dying sun. These silent sentinels of science, pointed towards the heavens, are constantly listening to the cosmic symphony that surrounds our planet. Welcome to Exploring the Universe. Today, we're going to uncover the fascinating world of radio telescopes, the true cosmic ears of astronomy that have revolutionized our understanding of the universe. These remarkable instruments have allowed us to peer through cosmic dust clouds, discover mysterious objects like pulsars, and even map our own Milky Way galaxy in unprecedented detail. In the next few minutes, we'll journey through the ingenious technology behind radio telescopes, exploring their essential components and discovering how they transform invisible radio waves into valuable scientific data. We'll uncover the groundbreaking discoveries they've made, from detecting the afterglow of the Big Bang to finding evidence of supermassive black holes at the centers of distant galaxies. We'll also explore how modern radio telescopes work together in vast arrays to create images sharper than any single telescope could achieve. But before we dive into this incredible technology that's reshaping our understanding of the cosmos, make sure to hit that subscribe button and ring the notification bell. Join our community of space enthusiasts here at Exploring the Universe, where we unlock the secrets of the cosmos together. Don't miss out on our weekly journeys through the most fascinating aspects of our universe. To truly understand radio telescopes, let's start with something familiar: the radio you might have in your car or home. Just as your radio picks up music and voice transmissions from local stations, radio telescopes are essentially enormous antennas that capture radio waves. But instead of listening to the latest hits, they're tuned to the natural broadcasts of the cosmos. Think of radio telescopes as super-powered cosmic radios. While your car radio might pick up signals from a few miles away, radio telescopes can detect incredibly faint radio waves that have traveled across millions or even billions of light years through space. These waves come from fascinating cosmic objects like distant galaxies, explosive supernovas, and even the remnants of the Big Bang itself. But you might wonder, why do we need these specialized instruments when we have powerful optical telescopes? The answer lies in the limitations of visible light. Imagine trying to see through a thick fog. It's nearly impossible because the fog particles scatter and block visible light. Similarly, in space, there are vast clouds of cosmic dust and gas that act like fog, making it impossible for traditional telescopes to see what lies behind them. This is where radio telescopes shine, or rather listen. Radio waves can pass right through these cosmic obstacles, allowing us to detect and study objects that would otherwise remain hidden from view. Furthermore, many of the most fascinating phenomena in our universe don't primarily emit visible light at all. Pulsars, for instance, are rapidly spinning neutron stars that beam out radio waves like cosmic lighthouses. Without radio telescopes, we would never have discovered these extraordinary objects. The same goes for the center of our own Milky Way galaxy, which is shrouded in thick clouds of dust, but broadcasts powerful radio signals that tell us about the supermassive black hole lurking at its heart. Another crucial advantage of radio telescopes is their ability to work 24/7. Unlike optical telescopes that can only operate at night and in clear weather. Radio waves penetrate Earth's atmosphere and even clouds, allowing radio astronomers to continue their observations regardless of local weather conditions or time of day. Just as different radio stations broadcast on different frequencies, cosmic objects emit radio waves across a wide range of frequencies. Radio telescopes are designed to tune into these various frequencies, giving astronomers a complete picture of the radio universe, from the low-frequency hum of ancient hydrogen gas to the high-frequency signals from newly forming stars. This basic understanding of radio telescopes opens up a whole new way of seeing, or rather hearing, the universe. These instruments have become fundamental tools in modern astronomy, allowing us to explore cosmic phenomena that would otherwise remain forever hidden from human perception. Just like a human ear collects sound waves and funnels them to our eardrums, a radio telescope is essentially a massive cosmic ear, carefully designed to capture and process radio waves from space. Let's break down the key components that make this technological marvel work. At the heart of every radio telescope is its most visible feature, the massive parabolic dish, or main reflector. This enormous bowl-shaped surface acts like a cosmic catcher's mitt, collecting radio waves from space. But it's not just a simple dish. Its precise parabolic shape is crucial. Just as a satellite TV dish focuses signals to a single point, this carefully engineered surface reflects all incoming radio waves to a precise focal point above the dish. These dishes can be truly massive. Some are hundreds of feet in diameter, and their surface must be incredibly smooth and precise, often crafted to tolerances smaller than the thickness of a human hair. Above the main dish, you'll find the subreflector, a critical component that might look small compared to the main dish, but plays a vital role. This secondary mirror is typically mounted on sturdy support legs and sits at a carefully calculated position above the main reflector. Its job is to catch the radio waves bounced up from the main dish and redirect them to the receiving equipment. Think of it as a precision mirror in a game of cosmic pinball, making sure the radio waves end up exactly where they need to go. The receiver is where the real magic happens. Positioned at the telescope's focal point, this highly sensitive instrument captures the concentrated radio waves and converts them into electrical signals. Modern radio telescope receivers are incredibly sophisticated, cooled to temperatures near absolute zero to minimize electrical noise and maximize sensitivity. They can detect radio signals so faint that they have less energy than a single snowflake hitting the ground. But collecting the signals is just the beginning. The data processing systems are the telescope's brain, turning these electrical signals into meaningful scientific information. These powerful computers process enormous amounts of data, often many gigabytes per second, filtering out interference from human-made radio sources, compensating for Earth's rotation, and combining data from multiple observations to create detailed radio images of the cosmos. To put this all together, imagine your ear but on a cosmic scale. The main reflector acts like the outer ear, collecting and focusing waves. The subreflector works like the ear canal, guiding these waves to their destination. The receiver functions similar to your eardrum, converting the waves into signals, and the processing systems operate like your brain, making sense of what's being detected. This entire system must work in perfect harmony, with each component precisely aligned and calibrated. The main dish must be able to point accurately at different parts of the sky, often tracking celestial objects for hours as Earth rotates. The surface must remain precisely shaped despite wind, temperature changes, and the constant pull of gravity. The electronics must function flawlessly while processing astronomical amounts of data. Modern radio telescopes often incorporate additional sophisticated systems, such as adaptive surfaces that can adjust their shape to compensate for distortions, and advanced cooling systems to keep the sensitive electronics at optimal operating temperatures. Some even work together in arrays, combining signals from multiple telescopes to act as one enormous virtual telescope, capable of producing images with incredible detail. This remarkable combination of components, working together with incredible precision, allows us to explore aspects of the universe that would otherwise remain completely invisible to us, revealing the dynamic and often violent processes that shape our cosmos. The story of radio astronomy begins with one of science's most fortunate accidents. In 1932, a young engineer named Karl Jansky was working for Bell Telephone Laboratories, investigating sources of static that might interfere with early radio communications. Using a rotating antenna system that locals nicknamed Jansky's merry-go-round, he detected a persistent hiss that seemed to peak every 24 hours. Initially, he thought it might be coming from the sun, but after months of careful observation, he realized something extraordinary. The signal actually peaked every 23 hours and 56 minutes, exactly matching the timing of the Earth's rotation relative to the stars. This revelation was groundbreaking. Jansky had discovered radio waves coming from the center of our Milky Way galaxy. He had opened an entirely new window to the universe, though few astronomers at the time fully appreciated the significance of his discovery. This static, this cosmic whisper that had initially been considered mere interference, would eventually revolutionize our understanding of the cosmos. Enter Grote Reber, an amateur radio enthusiast who became captivated by Jansky's discovery. In 1937, unable to secure funding from scientific institutions, Reber took matters into his own hands. In his backyard in Wheaton, Illinois, he built the world's first dedicated radio telescope, a 31-foot parabolic dish constructed from wood and metal sheets. Working alone, often at night to avoid interference from car engines, Reber created the first radio maps of the sky. His homemade telescope detected radio emissions from the Sun, the Milky Way, and several other bright radio sources, proving that Jansky's discovery wasn't a fluke, but rather the first glimpse of an entirely new field of astronomy. From these humble beginnings, radio astronomy has evolved dramatically. The post-World War II era saw rapid advancement as surplus radar equipment was repurposed for astronomical observations. The 250-foot Jodrell Bank telescope in England, completed in 1957, demonstrated the potential of large, steerable dishes. But astronomers wanted more. They needed better resolution and sensitivity to study fainter and more distant objects. This led to the development of radio interferometry, where multiple telescopes work together as one. By combining signals from telescopes spread across large distances, astronomers could achieve the same resolution as a single telescope, as large as the distance between the individual dishes. The Very Large Array, VLA, in New Mexico, with its iconic Y-shaped configuration of 27 dishes, became a symbol of this new era in radio astronomy. More recently, international collaborations have created virtual telescopes the size of our planet, able to produce images with unprecedented detail. Today's radio telescope arrays are technological marvels. Projects like ALMA in Chile's high desert and the upcoming square-kilometre array in Australia and South Africa represent the cutting edge of this technology. These modern arrays combine dozens or even hundreds of individual antennas, using sophisticated computer systems to merge their data into extraordinarily detailed views of the cosmos. And now, I'd love to hear from you. If you could point a radio telescope anywhere in the universe, what cosmic signal would you most want to capture? Maybe you're curious about the mysterious fast radio bursts, or perhaps you'd like to listen for potential signals from other civilizations. Share your astronomical aspirations in the comments below, and let's explore the possibilities together. The evolution of radio astronomy shows us how human ingenuity, persistence, and collaboration can unlock the deepest secrets of our universe. From a simple rotating antenna to vast arrays of sophisticated dishes, we've come an incredibly long way in our ability to listen to the cosmic symphony that surrounds us. Imagine a telescope so massive it could contain 450 football fields. That's the FAST telescope in China, currently the world's largest single-dish radio telescope. Nestled in a natural depression in China's Guizhou province, this engineering marvel spans 500 meters in diameter. What makes FAST particularly fascinating is its active surface. The dish is made up of nearly 4,500 individual panels that can be adjusted in real time, like a living, breathing instrument. The telescope is so sensitive, it could detect a cell phone conversation on a planet orbiting a star dozens of light years away. But how do radio telescopes actually create photographs of the cosmos when they're not collecting light, but radio waves? It's a fascinating process that's more like painting than photography. When radio telescopes collect data, they're essentially measuring the intensity of radio waves coming from different points in the sky. Computers then translate these invisible signals into visible images, assigning different colors to different radio frequencies or intensities. Think of it as translating a symphony into a painting. We're converting one type of sensation into another that our human brains can better understand. The discoveries made by radio telescopes have repeatedly revolutionized our understanding of the universe. One of the most dramatic was the discovery of pulsars in 1967 by Jocelyn Bell Burnell. Initially nicknamed "little green men" because of their incredibly regular pulses, these rapidly spinning neutron stars have become essential tools for testing Einstein's theory of relativity and might even help us develop future space navigation systems. Radio telescopes have also unveiled the mysterious jets shooting from the cores of galaxies. Streams of particles extending for millions of light years, invisible to optical telescopes but blazing bright in radio waves. They've helped us map the distribution of hydrogen gas throughout our galaxy, revealing the spiral arms of the Milky Way that we can't see from our position inside the galaxy. Perhaps one of the most profound discoveries was the cosmic microwave background radiation detected accidentally by Arno Penzias and Robert Wilson in 1964. This faint radio hiss, coming from all directions in space, turned out to be the afterglow of the Big Bang itself, the oldest light in the universe, giving us a baby picture of our cosmos when it was just 380,000 years old. Radio telescopes have even spotted complex organic molecules floating in space, suggesting that the building blocks of life might be more common in the universe than we once thought. They've detected bizarre phenomena like fast radio bursts, incredibly powerful flashes of radio waves that last for just milliseconds and whose origins we're still trying to understand. More recently, radio telescopes working together in the Event Horizon Telescope Array achieved something once thought impossible. They took the first ever picture of a black hole's shadow, showing us the environment around these cosmic monsters that even light cannot escape. The sensitivity of modern radio telescopes is almost beyond comprehension. The combined power of arrays, like the Very Large Array in New Mexico, could detect the heat from a snowman on Pluto, if there were any snowmen there. This incredible sensitivity means we're constantly discovering new phenomena and pushing the boundaries of our understanding of the universe. These discoveries remind us that some of the most important findings in science come from looking at the universe in ways that transcend our natural senses. Radio telescopes have shown us that the cosmos is far more dynamic, violent, and fascinating than we could have imagined by just looking at the night sky with our eyes alone. One of the most remarkable applications of radio telescopes is in the detection and study of pulsars, those cosmic lighthouses of the universe. These rapidly spinning neutron stars emit beams of radio waves with such precise regularity that they outperform even our best atomic clocks. Astronomers use these stellar timepieces for everything from testing Einstein's theory of relativity to potentially developing an interstellar GPS system for future space navigation. Each pulsar we discover adds to our cosmic lighthouse network, helping us better understand both the pulsars themselves and the space-time fabric they travel through. When it comes to studying distant galaxies, radio telescopes truly shine. Unlike optical telescopes, which can be blocked by cosmic dust and gas, radio waves pass through these barriers, revealing the hidden structures of galaxies billions of light-years away. This capability has revolutionized our understanding of galaxy evolution and cosmic structure formation. Radio telescopes have revealed massive black holes at galactic centers, detected the feeding streams of cold gas that fuel star formation, and mapped out the vast cosmic web that connects galaxies across the universe. Perhaps one of the most intriguing applications is in the search for extraterrestrial intelligence. Radio telescopes serve as our primary tools in the quest to detect potential signals from advanced civilizations. The logic is compelling. Radio waves can travel vast distances through space with minimal degradation, making them an ideal medium for interstellar communication. Projects like Breakthrough Listen use some of the world's most powerful radio telescopes to scan millions of stars for artificial signals that might indicate technological activity. While we haven't detected any definitive signs of extraterrestrial intelligence yet, this search has yielded valuable data about natural cosmic phenomena and pushed the boundaries of our signal processing capabilities. The mapping of our own Milky Way galaxy represents another crucial application. Radio telescopes have revealed our galaxy's true structure in ways optical telescopes never could. By detecting hydrogen gas emissions, radio astronomers have traced out the spiral arms of our galaxy, mapped the distribution of star-forming regions, and revealed the motion of gas clouds around our galaxy's central supermassive black hole. This work has transformed our understanding of our cosmic home, showing us that the Milky Way is a dynamic, evolving system with complex structures hidden behind visible light's limitations. Beyond these primary applications, radio telescopes serve numerous other practical purposes. They help track space debris that could threaten satellites, monitor solar activity that could affect Earth's technology, and study planetary surfaces through radar astronomy. Weather satellites use principles similar to radio telescopes to monitor Earth's atmosphere, and the same technology helps improve medical imaging techniques. In asteroid detection and tracking, radio telescopes play a crucial role in planetary defense. By bouncing radio waves off near-Earth objects, astronomers can determine their size, shape, and trajectory with remarkable precision, helping us identify any potential impact threats years or even decades in advance. The applications of radio astronomy extend into fundamental physics as well. By studying how radio waves behave near massive objects like black holes, astronomers can test the limits of our physical theories and search for deviations that might point toward new physics. The precise timing of pulsar signals, for instance, has already helped confirm the existence of gravitational waves, one of the most significant scientific discoveries of the 21st century. These practical applications demonstrate how radio telescopes have evolved from curious scientific instruments into essential tools for understanding both our cosmic environment and the fundamental nature of the universe itself. As technology continues to advance, new applications emerge, promising even more discoveries and practical benefits in the years to come. The process of converting radio waves into meaningful data is a fascinating journey that begins the moment a cosmic signal reaches Earth. When radio waves from space hit the telescope's dish, they're reflected and concentrated just like light in a mirror. But what happens next is where the real magic begins. These waves are directed to highly sensitive receivers that work a bit like the antenna and circuit in your car radio, but far more sophisticated. These receivers are so sensitive, they need to be cooled to temperatures near absolute zero to prevent their own heat from creating unwanted noise in the signal. Think of it like turning up the volume on a very quiet whisper. The original signal from space is incredibly faint, often millions of times weaker than the signals from your local radio station. The telescope amplifies these whispers, then converts them from waves into digital signals that computers can process. It's similar to how your smartphone converts sound waves into digital files, but with far more precision and complexity. The real breakthrough in radio astronomy came with interferometry. the ability to combine multiple telescopes into one virtual super telescope. Imagine an orchestra where each instrument plays the same piece of music. When combined perfectly, they create a much richer sound than any single instrument could produce. Similarly, interferometry takes signals from multiple radio telescopes and combines them with incredible precision, timing the arrival of waves down to billionths of a second. This technique allows astronomers to achieve something remarkable. Two telescopes working together can see details as fine as a single telescope, as wide as the distance between them. The Very Long Baseline Interferometry, VLBI, can link telescopes across continents or even in space, creating a virtual telescope the size of Earth itself. This is how astronomers captured the first image of a black hole, by turning our entire planet into one enormous radio telescope. Resolution and sensitivity are crucial factors in radio astronomy. Resolution determines how well a telescope can distinguish between two closely spaced objects, like being able to see two headlights on a distant car instead of just one blur of light. The larger the telescope, or the wider the spacing between interferometer telescopes, the better the resolution. Sensitivity, on the other hand, determines how faint a signal the telescope can detect. This is where the size of the collecting area becomes crucial. Bigger dishes can collect more radio waves, making fainter signals detectable. Modern radio telescopes achieve extraordinary levels of both. The FAST telescope in China, for instance, is so sensitive it could detect a cell phone signal on a planet orbiting a distant star. Meanwhile, interferometer arrays can achieve resolution fine enough to read a newspaper headline on the moon, if it were broadcasting radio waves. The data processing involved is equally impressive. A single observation can generate petabytes of data, millions of gigabytes, which must be processed to remove interference from human-made radio sources, compensate for atmospheric effects, and combine signals from multiple telescopes. Supercomputers run complex algorithms that can distinguish the faint whisper of a distant galaxy from the roar of earthly radio interference. To put this in perspective, when radio astronomers create an image of a distant galaxy, they're processing more data than all the digital photos posted on social media in a day, just to create a single picture that might show up in a scientific paper. This incredible technical achievement allows us to see the universe in ways that would be impossible with any other method. The development of new processing techniques continues to push the boundaries of what's possible. Machine learning algorithms are being developed to sift through massive amounts of data, looking for patterns that might indicate new phenomena, while quantum computing could potentially revolutionize how we process radio astronomy data in the future. Imagine trying to hear a whisper from across a crowded stadium during a rock concert. That's similar to what radio astronomers deal with when it comes to terrestrial interference. Our modern world is absolutely saturated with radio signals. Cell phones, Wi-Fi networks, television broadcasts, satellite communications, and even microwave ovens create a constant barrage of radio noise that can completely overwhelm the incredibly faint signals from space. A single cell phone near a radio telescope can be millions of times stronger than the signal from a distant galaxy that astronomers are trying to detect. This problem has become so severe that radio astronomers have had to take extraordinary measures to protect their observations. Many countries have established radio quiet zones around their major telescopes, large areas where radio transmissions are strictly controlled or prohibited. The National Radio Quiet Zone in West Virginia, USA, spans 13,000 square miles, where even wireless devices are restricted. Local residents within these zones often live with limited modern conveniences to help protect the sensitivity of these scientific instruments. The need for isolated locations presents its own set of challenges. The world's major radio telescopes are often built in remote locations, high deserts, isolated valleys, or even in space. The Atacama Large Millimeter Array in Chile sits at an altitude of 16,400 feet in one of the driest deserts on Earth. While these locations offer excellent observing conditions, they create significant logistical challenges. Staff must deal with extreme weather conditions, limited access to supplies, and the difficulties of maintaining complex equipment in harsh environments. The cost of building and maintaining radio telescopes is staggering. The FAST telescope in China cost approximately $180 million to construct, and that's just the beginning. These instruments require constant maintenance to maintain their precise shapes and alignments. The surface of a radio telescope must be accurate to within fractions of a millimeter. Imagine maintaining the smoothness of a mirror the size of several football fields. Temperature changes, wind, and even the weight of the structure itself can cause distortions that must be constantly monitored and corrected. Power requirements present another significant challenge. Modern radio telescopes use sophisticated cooling systems to reduce electronic noise in their receivers, often requiring them to be chilled to near absolute zero. The computing facilities needed to process the enormous amounts of data require substantial energy as well. A single day of observations can generate petabytes of data that must be stored, processed, and analyzed. Weather poses its own set of challenges. While radio waves can penetrate clouds, severe weather can still affect observations. High winds can distort the shape of telescope dishes or even force them to be stowed for protection. Lightning strikes can damage sensitive electronic equipment, and extreme temperatures can affect the precision of the instruments. The human factor cannot be overlooked either. Operating these facilities requires highly specialized personnel, engineers, technicians, scientists, and support staff who are willing to work in remote locations. Training and retaining qualified personnel adds significantly to operational costs. There's also the challenge of upgrading these facilities to keep pace with technological advances. The basic structure of a radio telescope might last for decades, but the electronics and computing systems need regular updates to remain competitive. These upgrades can cost millions of dollars and require careful planning to minimize disruption to ongoing research programs. International collaboration, while essential for many projects, adds another layer of complexity. Coordinating observations across multiple facilities in different countries requires careful scheduling, standardized procedures, and complex diplomatic agreements. Different time zones, languages, and technical standards all need to be managed effectively. Despite these challenges, the scientific community continues to push forward, developing innovative solutions and new technologies to overcome these limitations. The rewards, in terms of our understanding of the universe, make these efforts worthwhile, even as we continue to face new challenges in this rapidly evolving field. The future of radio astronomy is embodied in what might be humanity's most ambitious scientific endeavor yet: the Square Kilometre Array, SKA. This revolutionary project, currently under construction in South Africa and Australia, will create the world's largest radio telescope network. When completed, the SKA will combine thousands of dishes and up to 1 million low-frequency antennas, creating a collecting area equivalent to 1 square kilometre. This massive array will be so sensitive it could theoretically detect an airport radar signal from a planet orbiting a star dozens of light years away. The SKA represents a quantum leap in our observational capabilities. It will be able to survey the sky up to 10,000 times faster than any existing radio telescope array. This unprecedented speed and sensitivity will allow astronomers to create the most detailed map of the universe ever made, potentially revealing millions of previously unknown galaxies and offering new insights into dark matter, dark energy, and the evolution of the cosmos. Beyond the SKA, emerging technologies are reshaping the future of radio astronomy. Artificial intelligence and machine learning are revolutionizing how we process and analyze the enormous amounts of data these telescopes generate. Advanced algorithms can now sift through petabytes of data, identifying patterns and phenomena that human observers might miss. These tools are particularly crucial for detecting fast radio bursts, mysterious millisecond-long pulses from deep space that could hold clues to some of the universe's most energetic events. Quantum computing represents another frontier that could transform radio astronomy. These next-generation computers could process the massive data streams from radio telescopes in ways that are impossible with classical computers. This breakthrough could allow us to create real-time maps of the radio sky, potentially catching cosmic events as they happen. New receiver technologies are also in development, including superconducting detectors that can operate at even lower temperatures, further reducing noise and increasing sensitivity. These improvements, combined with advanced signal processing techniques, could help us detect increasingly fainter signals from the early universe. Looking ahead, these technological advances could lead to extraordinary discoveries. The SKA and future telescopes might detect the first signs of biological molecules around distant stars, potentially identifying regions where life could exist. They could observe the formation of the first galaxies after the Big Bang, helping us understand how our universe evolved from its earliest moments. We might finally solve the mystery of fast radio bursts, potentially revealing new physics or previously unknown astronomical phenomena. The increased sensitivity of future telescopes could also advance the search for extraterrestrial intelligence, allowing us to scan more stars than ever before for signs of technological civilizations. Perhaps most excitingly, these future telescopes might reveal entirely new classes of cosmic objects or phenomena that we haven't even theorized yet. Just as the first radio telescopes discovered unexpected objects like pulsars and quasars, the next generation might unveil equally surprising discoveries that could revolutionize our understanding of the universe. Space-based radio telescopes represent another frontier. By placing radio telescopes in space or on the far side of the moon, we could escape Earth's interfering radio noise completely. Several space agencies are already developing concepts for lunar radio telescopes that could observe the universe at previously inaccessible low frequencies. The future of radio astronomy promises not just technological advancement, but a deeper understanding of our cosmic environment. As these new telescopes come online and new technologies mature, we're entering a golden age of radio astronomy that could transform our view of the universe and our place within it. As we wrap up our journey through the fascinating world of radio telescopes, let's reflect on how these remarkable instruments have transformed our understanding of the cosmos and our place within it. Radio telescopes have become absolutely fundamental to modern astronomy, serving as our cosmic ears to the universe's grandest symphony. They've revealed a universe far more dynamic and dramatic than we ever imagined when we were limited to optical observations alone. Through these instruments, we've discovered pulsars, mapped our galaxy's structure, witnessed the deaths of stars, and even captured the first image of a black hole. They've shown us that the seemingly empty spaces between stars are actually rich with activity, filled with complex molecules, magnetic fields, and processes that shape the evolution of galaxies. Think about this. Every day, radio telescopes around the world are capturing signals that have traveled across millions or even billions of light years to reach us. These ancient messages from the cosmos tell stories of stellar births and deaths, of galaxies colliding, and of the very first moments after the Big Bang. Through radio astronomy, we've developed a profound connection to the universe that transcends our natural senses. We're no longer limited by what our eyes can see. We've extended our reach far beyond the visible spectrum, allowing us to explore the cosmos in ways our ancestors could never have imagined. Our ability to hear the universe through radio waves represents one of humanity's greatest scientific achievements. It's a testament to human ingenuity and curiosity that we've found ways to detect and decode these invisible signals from space. Every time we point a radio telescope at the sky, we're not just collecting data, we're participating in a cosmic conversation that connects us to the vast tapestry of space and time. This technology has not only advanced our scientific understanding, but has also humbled us by revealing the true scale and complexity of our universe. Radio telescopes have shown us that we're part of something far greater than ourselves, a dynamic, interconnected cosmos that's still full of mysteries waiting to be solved. They remind us that there's still so much to discover, so many questions to answer, and so many wonders to explore. And now, if you've been captivated by the incredible power of radio telescopes and want to continue exploring the mysteries of the cosmos with us, I invite you to become a permanent part of our astronomical community. Hit that like button if you've enjoyed learning about these amazing instruments. Subscribe to our channel to ensure you never miss our weekly explorations of space and science. Don't forget to turn on notifications. Just click that bell icon to stay updated about new content as soon as it's released. Remember, every like, subscription, and share helps us reach more people who share our fascination with the cosmos. Together, we can build a community dedicated to understanding our place in this vast and beautiful universe. Thank you for joining me on this cosmic journey, and I'll see you in our next exploration of the universe's greatest mysteries.